Well, welcome to our first lesson from Unit 1 on functions. Our learning targets for this lesson are to be able to describe the subsets of real numbers and also to identify and evaluate functions and then also state their domain. So to begin, I would like to go through and just review the real number system. I'm going to go through this fairly quickly. The real number system starts out with natural numbers. The natural numbers are the ones you learn when you are just a little kid. You start with a first birthday and then have a second, third, fourth. And the natural numbers are 1, 2, 3, 4, 5 up through infinity. We add 0 to that and it's called the whole number system. And then we recognize there are negative numbers on the number line. So when we add the negatives, those are integers. And then moving out further, we recognize there are numbers between the integers. And when we have fractions, those are called the rational number system. The irrationals are the weirdos. Those are the square roots and pi and weird stuff like that. And all of those together are called the real number system. And in words, okay, here are all of those in words. I'm not going to spend a lot of time reading through those. You can read through those. Same thing I just said in the last slide. Set builder notation. We're going to learn two different types of notation that we'll be working with. I like the interval notation better. These are two different notations, set builder notation and interval notation, but I want you to understand both of those and be able to work with those. And set builder notation uses these curly brackets. Now this first part of this notation is read the set of all x such that, or the set of the numbers x such that. This vertical line is the such that, and this just means it's the set of numbers x. And then you'll have some requirement in here, okay? X has some properties. This one says x is greater than or equal to -3 and it's less than or equal to 16. And then you'll have some property of real numbers. Sometimes you won't have this, sometimes you won't have this. But that one says x is an element of, z is called the rational numbers. So I think that was, I don't think that was in the last slide, but if you don't know what the symbols are, z is rational, excuse me, z is integers, n is natural, r is real, q is rational, and then irrational is I. So if you have questions on those, be sure to ask me in class. So interval notation is much simpler, easier to use, and it uses inequalities and then brackets. So when you have these square brackets, okay, those mean that the endpoints are included, and that is a bounded region. If we have curved brackets, those endpoints are not included, okay? So interval notation for each of these examples here, I'm just going to click through these. If it has an equal to with it, then that end of the thing has, the end of the interval has a square bracket. If it doesn't have an equal to, then it's a curved bracket. And the one thing I want to make sure that you know is that infinity is an unbounded region, an unbounded endpoint. Infinity will never have a square bracket. It always has a rounded or curved bracket. And so that's how each of these intervals would be represented. So here's some examples that I'll work through with you. Describe the set of numbers using set builder notation. So this first one is the set of all x such that. Okay, what kind of numbers do we see? Well, 1, 2, 3, 4, 5, those look like the natural numbers. Excuse me. So we could say x is an element of n. We could just leave it at that. We could say x is greater than or equal to 1, where x is an element of the natural numbers. That would also work. So either of those two examples or those two ways would work. Okay. Letter B, if we want to write x is less than or equal to 3, that's going to be the set of all x such that, you're going to start these all the same way. We're going to say x is less than or equal to -3, okay, where x is an element of, now they don't tell us what number system we're using, so we're going to assume that it's just the real number system unless we know more information. The last one, the set of all x such that, all multiples of pi. So we're going to say x is equal to pi times some number, where n is probably going to be an integer, a multiple of pi. And then we're going to say Um, x is an element of, and this one we're just going to call the real number system as well. Okay. Interval notation, much simpler. We just take our endpoints, -4 and -1, put a comma between them. If it has an equal to with it, like it does right here, that was not helpful there. Let me pick a different color here. If it has an equal to with it, let me use red, then that's a square bracket. You can see how this has less than or equal to. This one does not have an equal to, okay, right here. So this one's going to be a curved bracket. That's interval notation, much easier, right? This says a is greater than or equal to -3, so -3 is the minimum value, and then it's any value bigger than that, so it goes up to infinity. Infinity is never bounded. -3 is included, so that's a square bracket. This one says all the stuff that's greater than 9, so it goes from 9 to infinity. 9 is not included. The word or means union, okay? So that's going to be a big U is how we represent that. The next part says x is less than -2, so -2 is the biggest value, and that is not included. And negative infinity is to the left of -2. Now the one thing I want to mention on this problem is that these two things are in the wrong order. 9 to infinity is the right end of the line, whereas negative infinity to -2 is the left side, so we really should flip those around for it to make sense. And then 9 to infinity. Okay, if we want to be proper about the mathematics of that, we should write it that way. Functions are just a special type of relation where the domain value or the input value cannot go to more than one range value. And I like to think of functions, I think the easiest way to explain what a function is like a party. So we might have all these people in the domain, and there's 3 people having parties in the range. And if I say Joe and Casey and Stan go to Kevin's party, Laura's going to Holly, Zeke's going to Holly, Sarah and Anna are going to Marty, that is a function. Okay, every person is only going to one party. Now, what if I go in and do something like this? What if I say, okay, Joe is going to go to Kevin's party and Joe is going to go to Holly's party? Okay, that is no longer a function. Okay, that's not a function because you have one element in the domain going to 2 places, and that's not okay. You can have as many as you want going to the same place in the range. So in other words, I could have everybody going to one party. That's totally fine, but we can't have one person going 2 places in the range. Okay, so that would be a function, that representation there. We have several ways that we can model functions. I've listed 4 of them here. So one of the ways we can model functions is just using words. Another way to model functions is numerically or numbers. Often that's as ordered pairs. You might see it as a table or as just ordered pairs. We could also model them graphically, or we could model them using equations or algebraically. So if we want to determine if something is a function, there's different ways to do that. Letter A says the input value is the area code and the output is a phone number in the area code. Well, if we just use, say, area code 320, okay, can that go to more than one phone number? Well, obviously it does. It goes to a lot of phone numbers, right? I don't know, 333-1212, 333-1213. It's going to go to a whole bunch of, I must have hit my erase button there. Go to a whole bunch of different numbers. So that one definitely is not a function, okay? Letter B, how do we tell if it's a function when it's a graph? Well, hopefully you remember you do a vertical line test, and if it crosses more than once, that vertical line, it's not a function. This is not a function. Okay, letter C. When we look at letter C, we have an ordered pair, or several ordered pairs. If you look at the inputs, okay, the x values are all here. Well, these 2 x values are the same. And if they're the same and they're going to different numbers, that also is not a function. So none of our examples were functions. Function notation. You're probably familiar with function notation already. F of x is how we read the symbol f parenthesis x parenthesis. And f of x represents the value of the function at x. So it's actually an output. F of x means the exact same thing as y. Okay, so need to remember that. I also highlighted for you, x is always the independent variable and the dependent variable is y. So here's a few examples down below. If we want to find f of 12, make this just a little bit smaller here. F of 12 just means we're substituting in the value 12, okay, everywhere in the equation where there's a letter x, okay. So I'm just going to rewrite that as 2 times 12 plus 3 divided by 12 squared minus 2 times 12 plus 1. Well, in the top, 2 times 12 is 24 plus 3 gives us 27. In the bottom, 12 squared is 144. 2 times 12 is 24, and those are subtracted, and then plus 1. 144 minus 24 is 120, plus 1 is 121. So we get 27 over 121. Okay, so that's our answer for letter A. Letter B says instead of putting in a number, sometimes we might want to put in a number and a letter. So letter B, and I'm going to extend this a little bit because we might need the room. And I don't know if it does that on my video screen or not, but hopefully that works. Letter B, we're going to plug in 6x this time. So f of 6x, okay? So 2 times whatever x is plus 3 divided by whatever x is squared minus 2x plus 1. This time we're going to plug in the value 6x everywhere there was an x before. Whoops, skipped one right here. That should be a 6x, right? And then go ahead and multiply that through. So 2 times 6x gives me 12x plus 3. Denominator, 6x squared. 6 squared is 36. X squared is x squared. Then we get a 12x. So 36x squared minus 12x plus 1 is our answer. You should always check to see if this thing factors. In this case, it doesn't. There is a common factor of 3 in the numerator, but it doesn't really help us since the denominator doesn't factor. Okay, so let's move on to letter C. This time, we're actually going to substitute in negative 3a plus 8. So take a deep breath. Here we go. 2 times whatever x is, add 3. Denominator, whatever x is squared, minus 2 times whatever x is plus 1. So this time we're going to plug in negative 3a plus 8. Everywhere there was an x. And once we do that, now we need to multiply that through. Numerator, distributing our 2. Okay, good review of our algebra skills. Negative 6a plus 16 plus 3. Denominator, when we square a binomial, this thing's called a binomial. And when we square that, remember we have to use FOIL. So it's going to be negative 3a plus 8 multiplied by negative 3a plus 8. So multiplying our first terms gives us 9a squared. Remember, it's first times first. Our outside terms is negative 3a times positive 8, which is minus 24a. And then our inside term is also minus 24a. And our last term is 8 times 8 is plus 64. So that's just this thing right here. Okay. Then we're going to distribute a negative 2. So then we get a plus 6a. A negative 2 times a negative 3a is a plus 6a. Minus 16 plus 1. Holy moly. So 9a squared. Okay, got that guy. How many a's? Minus 24 and minus 24 and plus 6. Well, that's a minus 48a plus 6a. So that's a minus 42a. And then our constant terms, we have a plus 64 and a minus 16 and a plus 1. So 64 minus 16 is what, 48? and plus 1 is plus 49. Okay, so we have one term to combine right there, so we get negative 6a plus 19 all over 9a squared minus 42a plus 49. Final answer. All right, so just hang in there. Some of these will get a little bit long, but you have the skills to complete these. Sometimes we have to limit the domain of an equation for it to be a function. That happens when we can get a denominator of 0, or when we have a radical where we get a negative underneath the radical, okay? Taking an even root of a negative number. So let's jump into this one. Letter A, find the domain. So the only thing we really care about is what would make the denominator 0. We don't have any radicals in this one. So what would make that 0? Well, the easiest way to figure out what would make that 0 is to factor it. So our first terms are x and x, and then we want factors of 12 that add to 7. Well, factors of 12 that add to 7 are 3 and 4, and they're both plus. So to find out what makes that 0, set it equal to 0. So I would get x plus 3 is 0, or x plus 4 is 0. So x is negative 3 and x is negative 4. So these are the values we want to exclude. So we're going to say x cannot equal those two values. So any other value is fine, but x could not be those two. So that's how we limit the domain. Let's look at letter B. So this one, we can't have negatives under the square root. Well, what does that mean? That means a squared minus 4 cannot be equal to anything less than 0, so it has to be greater than 0. So solving this one, if you add 4 to both sides, we get a squared. It has to be greater than 4. And then take the square root of both sides. Those cancel out. They're inverse operations, and we get a has to be greater than plus or minus 2. So let's take a look at that. If we put in a value of 2, we get 0 under there, which is totally fine. But what if we put in a value of 1? If we put in a 1, 1 squared minus 4, and under the radical gives us a square root of negative 3, and that can't happen. That's why it has to be greater than 2. What about a value of negative 2? If we put in a negative 2 and square it, we're okay there, because that would give us a positive 4 minus 4, which is square root of 0. That's still okay. What if we put in a negative 3? Negative 3 should still be okay. Okay, so anything that's greater than positive 2. But what about, what if we put in a negative 1? Okay, so this is where I want to show you. If I put in a negative 1, okay, I still get that 1 minus 4 under there, and that gives me a negative. So a has to be greater than 2, and I don't know if you remember doing these complex or compound inequalities. A also has to be less than negative 2. Okay, so it's the stuff that's less than negative 2 and the stuff that's greater than positive 2. Well, that's really messy on my screen. So let's go ahead and clear that off a little bit. Working on letter C, this one we have a square root and a denominator. So what would make the square root negative? So 2x plus 6 has to be greater than 0. Again, so, solving for x, we end up with 2x being greater than negative 6, x greater than negative 3. But can x equal negative 3? And x cannot equal negative 3 because that would give us a 0, and we can't divide by 0. So as long as it's greater than negative 3, we're all right. So that one should be just x greater than negative 3. All right, so piecewise functions are functions that are defined by 2 or more equations for different intervals of the domain. And here's an example using speed. So we have these 3 equations for different values of the input, which is time. And the output here is a different equation based on what your input is. So this one, letter A, says we're looking to find the speed at each time. So we want v of 5. So 5 falls in this interval as an input. So we're going to use this function. So v of 5 is equal to 4 times 5, which is 20. Okay, v of 15, okay, it's equal to 15, so that's going to fall in right here as well. So again, that one's going to be v of 15 is equal to 4 times 15, which is 60. And the last one, v of 243, now 243 is in that interval, so we're going to use this function. So v of 243 is equal to negative 6 multiplied by what that value is, 243, and then plus 1500. Well, negative 6 times 243 is, let's see, I'm going to have that punched in on my calculator, negative 1458 plus 1500 gives us a final answer of 42. Here are a couple of problems for you to try. Please do these on your own. You can look at your notes, look at your video, look at anything in your book, and bring your answers to class, and we'll talk about it next time. See you next time.